Um, so welcome to the seminar today, and we are very happy to have Sergey from Montpellier, who is going to talk about something we are interested in to hear, his recent work on mathematics, topological invariance and connections with modularity of BPS black holes. Over to you, Sergey.
Thank you very much. First of all, thanks a lot for inviting me to speak at this seminar. It's a real pleasure for me. And I would like to present today kind of a review of the results of long-going projects, which I was doing with several wonderful collaborators who are listed here. And some of them already gave seminars at your channel, I think, but I hope to present things maybe from a little bit different point of view. Please interrupt me if there are any questions, I'll try to not go into much details, but mainly give main ideas and main results. But first, I would like to start from some motivation. Actually, what I'm going to tell you, it lies at the interface of physics and mathematics. So depending who you are, physicist or mathematician, you can have different motivations. But since I guess most people here are physicists, so let me give physical motivation. And the main motivation comes from the well-known problem of black hole entropy. Namely, we want to understand what are the microstates responsible for black hole entropy and how to count this entropy exactly, and not just in the approximation where the black hole is very large, where this famous Dickinson-Hawking formula is supposed to apply. And we know that string theory provides a very concrete answer to these questions, namely that if we consider, for example, black holes in a d-dimensional space-time, in the theory obtained after compactification of 10-dimensional string theory on some 10 minus d dimensional compact manifold, then from string point of view, this black hole at the microscopic level looks like a bound state of various branes wrapping non-contractible cycles on this internal compact manifold. And then the black hole microstates are nothing else but just different brane configurations. And if we want to count this entropy, we should just need to count these brane configurations. In this talk, I will deal with string compactifications with extended supersymmetry, so n equal 2 and higher, and with the black hole solutions which preserve at least a part of this supersymmetry, so the so-called BPS black holes. And for such black holes, actually, it's convenient to work with the so-called BPS indices, which count the states, but with the sign, depending whether fermionic or bosonic state. Of course, generically, this can give a number which is less than the total number of states, but we know that in many situations they actually coincide. And in any way, if we get, for example, exponentially growing index, we're sure that the number of states will also be exponentially growing. And these indices are very good to consider because they are known to be invariant under various deformations of parameters in our theory, so like string coupling or moduli. So we can go from weak coupling to strong coupling, and the index is supposed to stay invariant. You see here I put an asterisk that sometimes it's not true and the index does change, but the change happens in a very interesting controlled way. I will mention this later in my talk, and this phenomenon is actually very, very important. Moreover, it's very nice that these indices turn out to have various kind of dual interpretation. Namely, they appear to be equal to, at first sight, completely different objects. For example, it's typical situation in string compactifications that they turn out to coincide with some topological invariance of our compactification manifold. The prominent example will be that in n equal 2 compactifications, they will coincide with the so-called generalized Donaldson-Thomas invariants of Calabi-Yau threefolds. And these invariants, they're like holy grail for mathematicians, because mathematicians are very interested in finding these invariants exactly, but it's a very, very difficult problem, even for them. And then in some setups, they reproduce BPS indices in supersymmetric gauge theories or in the topological versions. Another prominent example is that, which will be relevant for my talk, is that they actually coincide with the so-called Waffa-Witten invariants of four-dimensional surfaces, which four-dimensional manifolds, which count the earlier characteristic or more generically even Ditti numbers of modular spaces of instantons of certain topologically twisted super-Yang mills, which is known as Waffa-Witten theorem. So you see, it looks like we have completely different theory, but the BPS indices turn out to be the same as these invariants. And all these relations, they suggest that maybe we can use them to uncover some remarkable symmetry properties of these indices, and maybe even to use these properties to find these indices exactly. And the symmetry properties, which I'll be dealing with in this talk, are the modular properties. So let me go to this topic now. And first, let's consider what happens in computations with high enough supersymmetry, like n = 8 or n = 4, which can be obtained by, for example, studying type 2, either on a 6 torus or K3 times 2 torus. And actually, in this case, we're in a very good situation, because we essentially know these indices exactly. The point is that in this situation, they depend just on a few combination of charges because of large duality group, which restricts the charge dependence of the indices. And they can be organized into nice generating functions. And all these generating functions essentially have been found explicitly. Let me give you just one example of 1/8 BPS black holes in computations with n = 8 supersymmetry. So the computation of the torus. And in this case, with our BPS indices depend just on one integer number, n. So we have just one generating function, which can be written like this. And it's known to be, you see, the ratio of some Jacobi theta function to the 6th power of Dedekind theta function, which are known functions, very well known. We know the asymptotics, so we can extract the asymptotics. And we find that it perfectly matches the prediction of Bekenstein-Hawking entropy, which can be computed from supergravity. So everything is nice. And the fact which is important for us is that the functions which appear here, this theta function and the Dedekind theta function, they're actually modular functions. Namely, they transform nicely under the standard fraction linear transformation, which forms the SL to Z group, which is the modular group of the torus, as you know. And generically, we say that a function H is a modular form if it transforms under these transformations covariantly. Namely, it's invariant up to this standard factor to the power W, and then we say that W is the modular weight of this particular modular form. In fact, we will need also a slight generalization of this definition, where we allow H to be a vector valued object. Namely, we put an index mu, which typically takes some finite number of values, and then we also allow in the transformation certain matrix, which is called multiplier system, and whose elements are usually just some simple phase factor.
So what does the small g denote?
An element of a cell to Z. So this matrix A, B, C, D.
Ah, okay.
G is just this 2x2 matrix.
I see.
So this multiplier system, it depends on the element on the transformation by which you act.
So it's a representation of the transformation, or some
Yes,
way?
yeah. So it's a representation of a cell to Z. Typically, it's the so-called wire representation.
I see. Thank you.
Okay, so yeah, so the situation which happens here is that our generating function is some modular form under SL to Z, is actually not an accident, but I'd like to say that this is a general situation in string theory, and one can say that the modular symmetry governs black hole entropy. And well, in the theories with n equal 4 and n equal 8, this is kind of expected because you see, we always have some torus in the game. And once we have a torus, it's natural to expect the modular symmetry, yeah, because this is the symmetry of the torus. But the whole idea of the project was to generalize these results to computations with n equal 2 supersymmetry, where at first sight you don't have any torus because you take just type 2 on a Calabi-Yau and we don't see any torus.
Again, I can have a very simple kind of simple-minded question. So this modular symmetry, is it an outcome of strong weak duality, this S duality, or is it something that is like that you cannot just explain by duality alone? Is it something that?
No, well, it will be related to S duality.
Yes.
Although once you, for example, work with this n equal 4 and n equal 8 situations, in principle, it arises just the symmetry of the torus. So it's well, it has different incarnation, I would say. So there is one incarnation where it appears as S duality, but for example, this here you can take type 2A. In type 2A there is no S duality, yeah. And then it appears just a symmetry of some part of the of your computification menu. So it depends on the duality frame where you work.
So it's like a T-duality then. It's like a T-duality in that case.
Yes. Yeah.
Okay. Nice. Thanks.
We'll see later this explicitly in the n equal 2 situation, how it appears. Okay, so that was my motivation, so here is the plan of the remaining part of my talk. So first, I will describe you a particular class of black holes which I will be dealing with, namely D4, D2, D0 black holes in type 2 and Calabi-Yau. Then I will argue that the generating functions of the BPS indices possess some remarkable modular properties, or more precisely, mock modular properties, which is a modification of the standard modularity. Then I will very briefly describe some of the applications of these results. And in the end, I will concentrate on one particular application of the modularity, namely when we evaluate exactly this BPS indices for a simplest class of Calabi-Yau threefolds, namely those which have just one Kähler mode. So let's start. So this is my setup. So I'm considering type 2A string theory compactified on a generic Calabi-Yau threefold. And as is very well known, in this case, in 4 dimensions, we find an effective theory, which is n equal 2 supergravity coupled to some number of hypermultiplets and vector multiplets. And this effective theory, in this theory, there are B2 plus 1 gauge fields, where B2 is the Betti number of our Calabi-Yau, where B2 vector fields come from B2 vector multiplets. And there is one addition, which is called graviphoton and comes from the gravitational light. And because we have this B2 plus 1 gauge fields, our BPS black holes are characterized by electromagnetic charge, which has 2 B2 plus 2 components. So I can write my charge vector in this particular form, where all components have a very clear physical interpretation. Because from the microscopic point of view, these black holes appears bound states of D6, D4, D2, and D0 branes wrapping respectively 6, 4, 2, and 0 dimensional cycles. And then the charge components here, they precisely correspond to the brane charges. For example, P0 is D6 brane charge, so it just gives the number of D6 branes wrapped on the whole Calabi-Yau. Let's say QA will label the 2 cycle wrapped by D2 brane, and PA labels the 4-cycle wrapped by D4 brane, and so on. And the BPS index in this case is, as I already mentioned, coincides with the generalized Donaldson-Thomas invariant of our Calabi-Yau threefold. Now, we're interested in studying these BPS indices, but we will concentrate on a particular class of black holes, namely those which arise from D4, D2, D0 branes. So in other words, I put D6 brane charge to 0. So this is the class which I will consider. And of course, as I showed in motivation, it's advantageous to work not with just a single BPS indices, but to organize them in some generating functions. Well, how can we do this here? Well, the simplest idea will be pick up one charge, let's say Q0, sum over this Q0 and get some function of parameter tau. But the problem is that if you do so, you get a function from which you don't expect any nice properties. Why? Well, first of all, you see, still depends on too many parameters, namely all the remaining charges, PA, QA, which are in principle large vectors, each has B2 components. And also, it turns out that this function secretly depends not only on tau, but also on the Calabi-Yau moduli, because these BPS indices are not really constant, but they are only piecewise constant. And this is because of the famous wall crossing phenomenon, which I'll now want to explain.
Sergey, I have a very clarification question. So why does the A indices for both P and Q run over B2?
This is just a fact of Kaluza-Klein reduction that you get B2 vector multiplets coupled to n equal to supergravity when you do this computation generic.
It's electric magnetic duality. Simple.
Yeah, and
No, I was just simply thinking about in the sense that if it is counting 4 cycles and 2 cycles, what they should be the same.
Yes. They both run. They both run our B2 values. They have B2 components, but they label respectively 4 cycles and 2 cycles. So you can have, well, like D4 brane can wrap 1 4-cycle, and D2 brane can wrap another 2 cycles, so they can be different. Yeah. So they don't need to be the same.
Okay, thanks.
From the 4D theory, it is like one is electrically charged and the other is magnetically charged. Yeah. If you take a pair from the 4D theory, the black hole.
Mm-hmm.
Yeah, I understand. I was just confused by why number of 4 and 2 cycles should be the same.
No. When did electron become monopole? They're not the same.
Mm-hmm. Okay.
The question was why the number of components of PA and QA are the same. Well, this is because for B2 is equal to B4 for Calabi-Yau. It's the Hodge diamond for Calabi-Yau.
Oh, okay, I understand. Okay, now it is fine. Yeah, okay. Okay. Yes. Okay, thank you.
Okay, so now let's return to this wall crossing. So why this happens? Well, it has very simple physical interpretation, because our BPS indices, they count not only single-centered black holes, but also multi-centered black holes, namely bound states of black holes. And when you have a bound state, it's very natural that for some parameters, it can be stable, and for some other parameters, it can be unstable. Yeah. So it can decay, and in this case, it will not contribute to the index. So in some region of the modular space, we do have a contribution to the index. In another region, we don't. So the whole modular space, therefore, is divided into different chambers, where BPS, in each chamber, BPS index can have different values. And all these chambers are separated by the so-called walls of marginal stability. So on one side of this wall, bound state exists. On the other side, it doesn't exist. And if you are interested in the position of these walls, it's also very easy to write an equation fixing their position. The equation just says that the sum of masses of the constituents should be equal to the sum to the mass of the bound state. And we know actually there are explicit formulas for the masses in terms of moduli, and you can compute this equation. Now, if you are not familiar with this phenomenon in supergravity, but you know supersymmetric gauge theories, for sure you will recognize this phenomenon, because it appears already in the famous Seiberg-Witten solution for pure C2 super-Yang Mills, where the modular space we know is just a complex plane, and this complex plane is divided into two paths by certain ellipse. And inside this ellipse, there is the so-called strong coupling region, where the BPS spectrum contains just one magnetic monopole and one diene. And outside this ellipse, which is a weak coupling region, the BPS spectrum is infinite. So you clearly see that the BPS indices change once you cross this curve. And this curve is nothing else but the wall marginal stability for this particular theory. And exactly the same happens in supergravity. And now one can ask the following question. Suppose we know BPS spectrum on one side of the wall, can we compute it on the other side? And actually we can, due to the famous Kontsevich-Sobelman formula, which called wall crossing formula, and which precisely allows to do that. And it's very universal. It applies everywhere, for supergravity, for supersymmetric gauge theories, for quivers, for everything. So all kinds of wall crossing work with this formula. And therefore, we turn out to be in a very good situation that it's enough to compute the BPS spectrum just at one point in the modular space, and then you can travel in the modular space. Just if you hit a wall, you just use this Kontsevich-Sobelman wall crossing formula. At least in principle, it's possible to do, and then you can compute the spectrum at any other point in the modular space. So therefore, it's enough to find it somewhere. And now I'd like to argue that there is one particular special point in the modular space, which is kind of distinguished by physics. And this is the so-called attractor point. So it appears due to the famous attractor mechanism, which exists in N=2 supergravity, which says the following. The point is that Calabi-Yau moduli, they appear from the four-dimensional point of view just some massless scalar fields. And in the black hole background, these scalar fields, they have some non-trivial profile. They can depend on the radial coordinate. But it turns out that independently how you fix them at infinity, which boundary condition you fix, they will always flow at the horizon to a fixed point. They will have a fixed value. And this value is completely fixed by the electromagnetic charge of the black hole. And it's called attractor point in the modular space. And therefore, it's very natural to define invariants, which we call MSW invariants due to Maldacena, Strom, and Cherenkov-Witten, which are independent of the moduli and which are just our initial indices evaluated at this particular point. So you see, they depend just on the charge gamma and nothing else.
And these are single-centered configuration.
Not all these.
Otherwise, otherwise the attractor story doesn't hold, right? You assume a radially symmetric.
Yeah, you are right, but actually, I'm a bit cheating here. Sorry, I didn't want to go to the subtlety. In fact, the point which we take here is not exactly attractor point, but is the so-called large volume attractor point.
So, but that will pick up set of charges, right? Only for some subset of charges will this attractor value be at large volume, right?
Yeah, yes. So it's not true attractor point, and therefore, in some situations, in particular those which will be relevant for us, it still can count still some bound states can contribute to it, because this is not true attractor point, but this large volume attractor.
Okay. So
yeah.
Yeah, no, the thing is, like, for instance, D6, D0, there is no single-centered solution at large volume, for instance.
Yeah, but
right.
For example, since we're considering D4, D2, D0, it
that problem is not there. This problem is not there. Yes, I know.
Yeah. Okay, so and another important feature of these indices, which is which appears here, is that actually the dependence on charges can be significantly reduced, because these indices turn out to be invariant under the so-called spectral flow, which acts on the electric charges in this way, where epsilon is an integer valued vector. And physically, this invariance just comes from monodromies around the large volume point in the modular space. And this monodromy changes the electric charges in this way, and the index should be invariant. So here I introduced a new notation, kappa AB, which is a certain quadratic form of this special indefinite signature, and which is defined by the intersection numbers of the Calabi-Yau, kappa ABC, and my magnetic charge. And since the omegas are invariant, you can easily conclude that they will depend only on the magnetic charge, P, on just one combination of electric charges, which stays invariant under these transformations. And in fact, you can also have dependence on the so-called residue class, which takes just finite number of values. So it takes just this number of values, which is determinant of this quadratic form. You can easily understand why this residue class appears. Take, for example, kappa AB to be even. Yeah? Then it's clear that you can never mix by this transformation odd and even electric charges. So there is some residue class which you cannot change by this spectral flow. And therefore, my BPS index still remains. But still, you see the number of parameters significantly reduced. And another important...
Can I ask one question? What is epsilon?
Epsilon is just a parameter of transformation, which is an integer.
Integer, right? Okay, yeah. So
it's an integer valued vector. Because
yes, yeah, okay, thank you. And one more question. So at large volume monodromy is usually transiting by some line bundle, if you think in terms of as some vector bundle or coherent sheaf, right? That's what the same thing is, right? This is what it is.
Yeah, mathematically it's realized by taking
okay
the line bundle.
And why are you calling it spectral flow? Is it some real spectral flow in some conformal field theory?
Yeah, because in this originally I think it appeared in this superconformal field theory studied by Alexandrov and Witten, and it was realized there as a spectral flow transformation.
Thank you.
And okay, so to continue, let me notice another important property, that this invariant charge, which I call Q0 hat, it's actually bounded from above, which means that if you take it to be very large, my index will always vanish. And this allows me to define generating functions of my BPS indices, which now you see depends on magnetic charge and this residue class. So I will think about it as a vector valued object. So HP is my vector valued function. Yeah, here I don't define what I mean by omega bar. Well, roughly speaking, if these guys are integers, so there is some standard way to define rational invariance from these integer ones. I don't write the formula, but it's very simple, and there is a one-to-one relation between these indices. It just appears that these guys are more convenient for the point from the point of view of modularity. And of course, my expectation is that these generating functions will have some nice modular properties. But now you can ask why? Why do I have? Why should I expect these modular properties at all? Because as I mentioned, we're compactifying our theory on generic Calabi-Yau. There is no torus in the game, so why you should have modular symmetry? Well, in principle, an argument for modularity was already given by Alexandrov and Witten, who showed that these functions, they appear in the so-called theta decomposition of the elliptic genus of certain CFT, and therefore it must be modular. But it turns out that this wall-sheet argument, it works only in a particular case where the divisor specified by magnetic charge P is irreducible. Namely, it cannot be decomposed as a sum of other four cycles. And only in that situation, this argument actually is correct. And now I would like to show you how one can derive exact modular properties of these generating functions based on a target space picture. So for this, let's again,
Sergey, can I ask a simple question? What determines Q0 hat max? The limit, the bound on Q0 hat, what is the constraint? In the sum, in the definition of HP mu.
Yeah, what is the value of this guy?
Yeah, what determines the value? Yeah.
Well, it's just fixed in terms of the second Chern class of the Calabi-Yau and this kappa ABC.
Okay.
So and magnetic charge. So it's well, it also has some mathematical meaning, some name, but I just don't remember.
Okay. Okay, doesn't matter.
Called,
okay.
I think it's called Bogomolny bound.
Oh, Bogomolny bound. Okay, got it. Okay, thanks. So some stability condition in some sense.
Yes. Yeah. Okay, so let's continue and let's consider again our setup, which is type trade on a Calabi-Yau. But we know very well that this is the same as M theory on a Calabi-Yau times a circle. And now let me do a trick. Let me compactify this theory on an additional circle. So then we get already an effective theory in 3 dimensions. And in 3 dimensions, this effective theory is nothing else but some supersymmetric nonlinear sigma model whose effective action is characterized by the target space of this sigma model. Yeah, so, namely the target, the metric on this target space defines for you the sigma model. It appears just a coupling for in the kinetic term for a bunch of scalar fields defining this sigma model. Okay, now, but now you see that we do have a tools in our story once we compactify this additional circle, and it has a modular group. And it means that this model group somehow be manifested in our effective theory. And the claim that it does, and it restricts my model, this target space of the sigma model to carry an asymmetric action of this SL to Z symmetry group. So that's the claim. And actually, this you can arrive to the same conclusion from this side if you apply T duality along this additional circle. Then you go to type 2B. And in type 2B, you know there is S duality. And then this, of course, gives exactly the same effective theory in 3D. And again, S duality is manifested as requirement of to be an isometry of this model. Of this target space, sorry. And now let's look what happens with our black hole. So I remind you that our black holes, they were defined as D4 brains wrapped on certain 4 cycle. So, and D4 brane has a 5-dimensional wall volume. So after computation of 4 cycle, you still have 1 dimension, yeah? Non-compact dimension. And now, after we introduce this circle in the game, let's require that this additional dimension of D4 brane is also compactified on this circle. It means that from the 3-dimensional point of view, our object will look like, well, it will be 0-dimensional, it will be like point-like. It will, and physically, it gives an instanton. And these instantons, they affect the metric on this model, on this target space, and namely, they induce instanton corrections. And what is nice is that each of these instantons is weighted by precisely our BPS index. Again, it's very easy to understand why, because our BPS index, just roughly speaking, counts the instantons of our particular charge gamma. So it's natural that all these instantons are weighted by the number of them. Yeah. And another good news is that all these instanton corrections we know explicitly. Namely, we computed the metric, the full instanton corrected metric like 15 years ago. So we know this metric. So you see now we're in a situation where we know the metric, which depends on BPS indices. And on the other hand, it must carry an isometric action of SL to Z. And of course, for generic values of BPS indices, it will not be true. This SL to Z must somehow constrain them. Or more precisely, one can derive constraints on the generating functions. Of course, it's easy to say, and it's clear that there should be some constraints, but actually it was the main non-trivial step of the whole project to derive these constraints explicitly. And it's really remarkable that it can be done to all orders in instanton expansion, in string coupling. So this can be done. So let me first explain you the result qualitatively. So what it implies. And first of all, so the result crucially depends on the properties of our force cycle. So if force cycle is irreducible, as I said, it cannot be decomposed into a sum of other force cycles, then indeed, in agreement with the Maldacen and Strominger-Witten, one can show that our generating function must be a vector-valued modular form. On the other hand, if the cycle is reducible, there is a modular anomaly. So our function is not truly modular. But one can construct a certain modification of this function, which will now be already non-holomorphic. So it will carry dependence on tau bar. So it's called non-holomorphic modular completion. So it will be such that this modification will be already true modular form. And what we have found, we have found an explicit formula for this non-holomorphic modular completion. I will not show you, will not explain in detail this formula, but just would like to give you its general form, because to explain it, it will take, I don't know, 15 minutes to introduce all ingredients. So let me just explain the general form. And the general form is very simple. So there is, first of all, the original function plus correction. And this correction has a simple physical meaning. You remember that our BPS indices include contributions from bound states. When our divisor can be decomposed into a sum of other divisors, it means precisely that there are contributions from bound states. And what is written here, this huge last term, is precisely the sum of the bound states, where n is, roughly speaking, the number of constituents. Then you see that I sum over decompositions of the total charge into charges of the constituents. And in the end, I take the product of generating functions representing these constituents. And the most non-trivial part is the kernel, which I use to sum these products. And the kernel consists of two parts. One is the exponential of certain definite quadratic form, but that's easy. And the most non-trivial thing is this function Rn, which in particular carries the non-holomorphic dependence of tau. And we have an explicit formula for this function. It's quite complicated, but roughly speaking, it's given by sum over a certain class of trees, which are all weighted by some derivatives of the so-called generalized error function. As the name suggests, it's some generalization of the well-known error function. So roughly speaking, there are some repeated integrals of the quadratic exponential. And the claim is that if you build such a function, it will be true modular form of this particular weight determined by the second Betti number of the Calabi-Yau. To make it a little bit more explicit, let me show you how this function looks in the most simple case, n equal to 2. Let me also, before say an important thing, that although here you see the sum goes from 2 to infinity, in each concrete case, the sum is finite. So if your divisor can be decomposed as a sum of n irreducible divisors, the sum will go up to this n and not more, because you don't have more complicated bound states in this case. So let's suppose our divisor can be decomposed just into two irreducible divisors. Then only function R2 is important. And here I showed its explicit expression. It's given by this function beta 3/2, which is just complementary error function and the exponential. And the exponential is just the derivative of this error function. And if you wish, you can write also explicit expression for the holomorphic anomaly of this completion. So you see, it's sufficiently simple. Okay, so you can say you showed me some crazy formula. Why is it nice? What does it mean? And now I'd like to argue that it's very nice from mathematical point of view, because mathematically these results imply that our generating functions are actually examples of the so-called higher depth mock modular forms. So what does it mean? So probably you heard that the mock theta functions first appeared 100 years ago in the last works of Ramanujan, but they were really mysterious for mathematicians. Mathematicians for almost 80 years, they understood there are some beautiful functions, there is something special about them, but there was no general theory of such functions. And such general theory was developed by Zwegers in 2002. And according to this theory, a mock modular form is a holomorphic function, which is kind of almost modular. Namely, it does have a modular anomaly, but this modular anomaly is of very special type. It's given by this integral, which is where you integrate another modular form, which is called shadow. I call it G here. And this modular anomaly in particular implies that you can construct in a standard way the modular completion, which will be already a true modular form, but will be non-holomorphic. It will be given by the same integral essentially, but just with the low limit given by tau bar. So you see, either you have a holomorphic function, but which is not modular, or you have non-holomorphic function, but which is modular. You can switch from one to another. And so this gives definition of mock modular form, and in recent years also higher depth mock modular forms appeared. And
Sergey, can I ask something before that? So what was the shadow in the previous example? You gave an example of a depth 1 case, right? So that was just some theta function?
Yeah,
this is the shadow is the one on the right here, right? In some sense.
Exactly. The shadow is this function, and actually here the situation is a little bit more complicated, and which will be important in the following, because usually you see here the shadow is anti-holomorphic. Depends on that. But here it's a product of holomorphic and anti-holomorphic pieces, because all these guys, they depend just on tau, and here you see tau 2, so you can decompose it as tau minus tau bar. So product of holomorphic and anti-holomorphic pieces. So the shadow will be a product of two modular forms. One is holomorphic and another one is anti-holomorphic. And such functions are called mixed.
So it's a mixed mock modular form. Okay. Got it. Yes. Okay, thanks.
Yeah. And precisely such mixed modular forms, they have generalization to high depth. Namely, this high depth is defined just iteratively. So you say that my mock model form has depth n if the anti-holomorphic derivative of the completion is expressed via mock model forms of less depth, depth less than n. So it's an iterative definition. And in our case, if the divisor is decomposed into n irreducible divisors, then the depth of our generating function is n minus 1. So, for example, if it's irreducible, the depth is 0. This is usual model form. If n is equal to 2, we get the usual mock model form, and so on. So this is description of kind of our main result. So if there are any questions, please ask. Otherwise, I will move to the applications. Okay. So let's discuss some applications, just very briefly. I will not go into details. Well, actually, the first application already appeared in the course of this project. Namely, it's application pure mathematics, because by realizing this project, we solved a long-standing mathematical problem, namely how to construct non-holomorphic completions for the so-called indefinite theta series. So they have these are theta series defined by quadratic forms of indefinite signature. And when the number of minuses was just 1, this case was understood by even before Zwegers. So these are examples of mock model forms, one of the most standard examples. But when there are 2 or more minuses in the signature, it was mathematicians didn't know how to proceed in this case. And somehow string theory produced automatically answer to this question. It produced for free the form of the non-holomorphic modular completion, and in particular, this result led to the development of the higher depth mock modular form. then there is another, well, it's rather extension, not application, but which will be important for other applications. Namely, it turns out that this construction can be extended to include the so-called refinement parameter. So it turns out that our indices can be generalized, and instead of summing just -1, you can sum -y to the power 2g3. G3 is some angular momentum. These are called refined BPS indices. And it turns out that the whole construction generalizes to include this refinement parameter. Why it happens, we don't understand, because we don't have an underlying kind of S duality, which kind of requires that such generating functions, which includes the refinement parameter, must be modular. But somehow we see that this construction exists and it produces many nice and correct results, which have been tested against other methods. So it works. And how it works? The claim is the following, that if you introduce these generating functions, which include this additional y-dependent factor, then they will be Jacobi mock modular forms. If this additional refinement parameter, or more precisely its logarithm, transforms as an elliptic variable. And you could think that introducing an additional parameter in the game, you complicate the story. So in particular, the formula for the completion will become even more horrible, but in fact, not. It crucially simplifies it. So the formula for the completion becomes much more simple. In particular, in this case, you sum only generalized terra functions, but not the derivatives. All the derivatives disappear. And also the class of the trees over which you sum simplifies enormously.
And what happens? Does mu, what is the index then? Index of the Jacobi form? That is mu, is it now?
No. Mu is the vector value.
Vector, yeah. Okay.
Yeah.
So what is the index?
The index is again defined by like second term class and intersection numbers of the Calabi-Yau.
Okay.
Yeah, so, and this construction was actually very helpful and instrumental in other applications. So one of them is applications to higher supersymmetry. With Suresh Nampuri, we show it that if we start from this refined construction and extend it to cases with high supersymmetry, n equal 4, n equal 8, all standard results about modular properties of BPS indices in this case just follow from this single formula for the completion. Well, of course, in n equal 4, you know that there are modularities with respect to SP4 largest symplectic group. Okay, this we cannot show, but all modular properties with respect to standard SL to Z, they all follow. And we not only reproduced known results, we also found something new, namely in the computations with n equal 4 supersymmetry, the generating functions of the so-called immortal dynes is known to be mock modular form. So its completion has a holomorphic anomaly, but the equation for this holomorphic anomaly, at least in the literature, we found it only for the particular case where the so-called torsion invariant constructed from electric magnetic charges is equal to 1. And we generalized this holomorphic anomaly to arbitrary torsion.
Sergey, is there some argument why this refined generating function would be a Jacobi mock modular form?
Well, as I told you, we do not have underlying physical reason. We don't understand it. So, but we see that there is a natural kind of upgrade of our unrefined construction to include the refinement. So it's kind of mathematical observation.
I see. That's a mathematical. Okay.
Yeah. It's a very interesting problem to understand why it is so, but we don't.
Okay, thank you.
And another application where this refinement was also very useful is application to Waffa-Witten theory. Let's take our Calabi-Yau, which is elliptic fibration over some surface, and take the limit where the fiber becomes very large. And then, so then you, of course, have non-compact Calabi-Yau, and mathematicians prove that if you impose this conditions on the surface, on the base of our vibration, then our DT invariance and also the refined version coincide with the Vafa-Witten invariance of the Vafa-Witten theory defined on these surfaces. Let me give you just one more detail how it works, the duality. Namely, in this case, there is only one, after you take the fiber to be very large, there is only one force cycle in the game. This is our base S. So all magnetic charges, all de Forbrin charges will be proportional to each other. Yeah, they will be proportional to the class S. So they are characterized by just one number, degree of reducibility, n. And this n is precisely the rank of the gauge group in the Vafa-Witten. And I claim that using our formula for the completion, one can actually derive explicit expressions for the generating functions of the Vafa-Witten invariants themselves for all n. Before they were known just for some low n, like n equal 2 was found by Vafa-Witten, then n equal 3 case was studied, but now one can derive them for arbitrary n, for the whole class of surfaces. So I think it's quite powerful application. But this is the case of non-compact Calabi-Yaus. And you know, in non-compact cases, there are some, well, many simplifications, but the real challenge is to do the same for compact Calabi-Yaus. And so this is the main interest from the physics point of view and also for mathematicians, because then we would be able to find this Donaldson-Thomas invariance for compact Calabi-Yaus. So in the end of my talk, I will briefly describe what we have achieved in this direction. So let's first of all consider what are the complications comparing to the non-compact case. Well, there are two complications. Well, first of all, I told you that to get these results for Vafa-Witten, the refined construction was important because it's much simpler, as I mentioned. But the problem is that the status of refined invariance for compact Calabi-Yau is not even clear. So it's not clear even whether they are defined mathematically. And also from physics point of view, it's not clear that they really exist. So we see that the construction seems to exist. It can be applied to many cases, but what it really means, as I mentioned, we don't understand. Also, its mathematical status is not clear. And another important thing is that in the non-compact case, there is a universal formula for the generating function for the irreducible case, n equal 1. There is a universal formula for this generating function. And in the compact case, there is no such universal formula. So this function with n equal 1 was a kind of seed for the whole construction, because all other functions are determined by this case, this irreducible case. So before even attacking the problem for reducible divisors where we have mock modularity, we have to understand, we have to find the generating functions in this pure modular case, n equal 1. So let's first study this case. And just to recall you, so in this case, we have a generating function, which is a vector value function defined like this, and it must be weakly holomorphic vector value at modular form of this way. By weakly holomorphic, here it just means that when you do Fourier expansion, there are terms with the negative power of Q. And by the way, in particular, these terms, they cannot be single-centered black holes. They correspond to bound states. And there is a remarkable result that actually the space of such functions is finite dimension. And the dimension of the space is not bigger than the number of polar terms, namely those terms which have negative power of n. I call them polar terms, and their coefficients polar coefficients. So you see that it's enough to find just these polar coefficients, and then in principle, it's enough information to completely fix the full generating function. Therefore, our problem is just to find these polar coefficients, so some number of Fourier coefficients for low charges, n. And we have addressed this problem for the simplest class of Calabi-Yaus, namely the ones which are smooth in complete intersection Calabi-Yaus in weighted projective spaces and have just one Keller model. And in total, there are 13 such Calabi-Yaus. And actually, 5 of them have been already studied in the previous lecture. And our results will perfectly match these previous results. So how we proceed? Actually, to do this, we had to use very recent mathematical results, mathematical understanding of these BPS indices. So let me try to explain this new mathematical stuff. So first of all, one should understand that our BPS indices are defined by certain stability condition. We just, well, physically it's clear. It just says which bound states are stable and which bound states are not stable. Yeah, and mathematically it's realized, but this stability condition is fixed by the so-called central charge function, which is just this is precisely the central charge which fixes the subgroup of supersymmetry which remains unbroken by our black hole solution. And it's just a linear combination of electric and magnetic charges. But in physics, we always have that, whereas electric charges are, the coefficients here are our moduli, so Keller moduli, the coefficients of the magnetic charge are given by derivatives of the holomorphic prepotential. This is the function which fixes our, which defines the geometry of the Keller moduli space of the Calabi-Yau. So it's the function which we know explicitly. But mathematically, so you see that this central charge depends only on Z. But mathematically, it's not necessary. We can be more general. We can work with more general stability conditions, and it's not necessary to take F to be function of Z. We can consider F as independent coefficients. And this gives rise to a larger space of stability conditions, which is called bridge and stability conditions. And the physical stability just defines a certain slice, a certain slice in this large space. And but there are other nice slices. For example, there is the so-called new BW stability, which appears just on the boundary of the allowed space of stability conditions, which has the following two features. Here, it coincides essentially with the physical stability. So this is the large volume region, precisely which we're interested in. But then somewhere here, it has another region where all BPS indices with respect to this particular stability, they vanish. But then we can come to the following idea.
So is that Giesecker stability? When you move away from large volume, does it become Giesecker stability?
No, it's what do you mean Giesecker stability?
Giesecker, I don't know how to pronounce his name. G-I-E. I don't know.
No. Giesecker is essentially Giesecker almost coincides with our physical stability. No, this is some new stability.
Oh, okay.
Yeah, it's very different. Yeah, and yeah, and then we come to the following idea: just start in this chamber where all indices are zero, and just move to this region using Kotsevich-Soibelman wall crossing formula. At least in principle, it should be possible. And then you compute the index here, and it coincides with the physical index. This is what we need. And this program has been realized for one modulus Calabi-Yaus by Sahel Feisbach, who derived an explicit formula relating our MSW invariants to the so-called Padharipan-de-Thomas invariants. And these guys are just our generic BPS indices with D6 brane charge equal to -1. And now we come to the following procedure. So let's start from the famous Gopakumar-Waffe invariants. You remember that they appear in description of topological string. Namely, topological string is a generating function. Partition function of topological string can be thought as generating function of Gromov-Witten invariants, but it can also be rewritten as in terms of Gopakumar-Waffe invariants. And this invariance can be found by the so-called direct integration of topological string, which essentially you take holomorphic anomaly equation for the topological string partition function, you solve it, you supplement it by boundary conditions fixing the holomorphic anomaly, and this way you find explicit expressions for each genus. You find explicit expression for topological string partition function. You expand and you find GV invariance. Then there is the so-called MNOP formula due to Maulik, Nekrasov, Okunkov, Podkharipande, which is by now a mathematical theorem, which allows to relate GV invariance to Podkharipande-Thomas invariance. And then we use this Bach formula to compute our invariance. So you see, there is a very direct procedure to arrive to our invariance. And this procedure has been, well, we followed it, and let me now explain the main results. So first of all, it's clear that the higher charges you need here, the more GV invariance you need to compute for higher genera. And this is very difficult. Even on Mathematica, it's very difficult to realize. It takes a lot of time and so on. And we have actually improved this direct integration method quite crucially, so that we could reach, for most of our 13 Calabi-Yaus, we could reach the maximal genus available by this direct integration method. You could ask why there is at all such maximal genus. Well, the point is that, as I told you, to solve topological string, you need not only to solve holomorphic anomaly equation, but you need a boundary condition fixing holomorphic anomaly, holomorphic ambiguities. And the point is that there are just finite number of such boundary conditions. So at some point you exhaust all of them, and you don't have enough data to fix holomorphic ambiguity, and you cannot provide full solution. Therefore, there is a maximal genus which is available for this method, and we achieved. So we computed all GV invariants up to this maximal genus for most of Calabi-Yaus. And using this data, we computed sufficiently many PT invariants and all polar terms for 11 out of 13 Calabi-Yaus. For 2 Calabi-Yaus, the data are not enough to get all polar terms. But for 11 Calabi-Yaus, yes. And moreover, for most of them, we computed not only polar terms, but also some non-polar terms. And now you can check this computation against prediction of modularity, because once you have all polar terms, you can compute the generating function, you can expand it, and you can get modularity predictions for non-polar coefficients and check them against this direct computation. And all this worked for many coefficients, which are crazy numbers with, I don't know, 14 digits. They perfectly coincided. So it was really like a miracle. And moreover, you can go, in principle, since you know generating functions, you can expand them to any, to arbitrary order in Fourier, and you get in this way infinitely many predictions for this MSW invariant. So all of them you essentially know. But now you can do even something new. You can go back. You can, using this prediction, you can compute PT invariance and then GV invariance. And in this way, you provide new boundary data for direct integration method. And it allows to go beyond the limitations of this direct integration method. And we did it for several Calabi-Yaus, and for example, for quintic, whereas direct integration allows to compute GV invariance up to genus 53, we managed to compute them up to genus 60. In principle, maybe one can go a little bit higher. Okay, that's all what I want to say about this case. And can I have 3 more minutes? Or then I can.
Yes. Yeah, you can even take 10 minutes more.
Okay. Then I would like to also tell you what happens if you go to the next level, n=2, where we do have mock modularity. But I will still stay in the case of one modulus Calabi-Yaus. So let's go to this next level where we have our generating function is a mock modular function. So then, in fact, due to the fact that this is not just mock, but mixed mock, that's important. The polar terms are not enough to fix this generating function. But what you can do, you can decompose the generating function into a piece which is pure modular, and in principle fixed by just finding the polar terms, and a piece which is some specific mock modular form with a specific modular anomaly. And now the question I would like to ask, can we find this specific modular form so that it satisfies our specific modular anomaly? And then the whole problem of finding the full generating function will be reduced to finding this guy, namely to fixing the polar term. So we will essentially return to the previous case. And the fact that it turns out that this is possible, again, due to our formula for the completion, which in this case of one modulus Calabi-Yau can be written like this. So in this case, the de-Fourier charge is equal to 2. So it's expressed in terms of generating functions, which we found at the previous stage with de-Fourier charge equal to 1, which are pure modular forms. And here I have a certain kernel, which must be another mock modular form, but with a much simpler modular anomaly, or equivalently, you can re-express in terms of its completion, and then this completion should have the following holomorphic anomaly. And you see, it's already much simpler, so I factorized all factors h1, and the anomaly is given by just very simple theta series. And also note that I put here index kappa. So kappa is the intersection number of my Calabi-Yau. I remind you, we have one modulus, so we have just one intersection number. For example, for quintic, it is equal to 5. Yeah. But now you can notice that if you put kappa equal to 1, this holomorphic anomaly equation is solved by the so-called generating series of Hurwitz class numbers, which is a very well-known function for mathematicians. It's one of the classic, very classic examples of mock modular form. It appears also in the work of Waffer-Witten, so everywhere. And for kappa equal 1, this is our solution. So we know G mu, so we can substitute here, and so we get this anomalous piece. And now you can ask what happens for other kappas. Well, and for other kappas, the solution can be generated out of this solution by applying certain generalized Hecke operator. So the thing here is that this index mu, it runs from 0 to 2 kappa minus 1, so it has 2 kappa values. So for kappa equal 1, this is a 2-dimensional vector. But for larger kappas, it's a high-dimensional vector. Yeah. And what the Hecke operator does, it essentially maps a modular object in one representation to a modular object in another representation. And here we use this fact to precisely build our solution, so one can check that this guy satisfies the required anomaly equation. And so in this way, we find our anomalous piece, and we see that the whole problem reduces just to the problem of finding the polar terms. And that's it. So I essentially finished. So let me just pass to conclusions. So the main result which I present you was an explicit formula for the modular completion of generating functions. So black hole degeneracy. So from mathematical point of view, DT invariance. And it worked for arbitrary divisor of Calabi-Yau. And the result is that the generating function is a high depth mock modular form. And this result already has many applications ranging from pure mathematics, complications with high supersymmetry, with Waffer-Witten theory, and ending by explicit evaluation of these BPS indices for compact Calabi-Yau. There are, of course, many further directions for this line of research, like one can generalize to more general types of Calabi-Yaus. Then it would be nice to understand all these results just from the worldsheet point of view, a la Maldacena, Strominger, and Witten. This is not done yet. And what I also mentioned several times is that we don't understand neither geometric nor physical meaning of the refined construction. Although this construction seems to be even more fundamental in a sense, but we don't understand its physical origin. So thank you very much for your attention. I stop here.
Thanks for this talk, Sergey. Thanks a lot. So now we can have more questions.
Yeah, actually going back to that, the extra variable Z, which you introduced to go to a mock Jacobi form, right? Right? That's what you got. Can you explain how you determine the index for that thing?
Well,
or is there a simple formula? I mean, you said it in words. I didn't remember. I didn't catch it.
Yeah, it's yeah, there is some I just forgot the name for this mathematical object which gives the index. So mathematically it's some either well, the formula is very simple. It's given by like intersection numbers contracted with the magnetic vector.
Okay.
Plus second term class also contracted with the magnetic vector.
Okay.
And divided, each of these terms is divided by 6 or 12 or something like
Okay.
that.
Okay. Okay.
So, and it's an integer. So
Thank
it's some topological invariant, which
Mhm.
either it's earlier characteristic of the divisor or one of these. Yeah, just sorry, I forgot the proper mathematical name for this object. And we determined it. Well, there are two things. So first, part of it, namely the part which depends, the first term, which depends on intersection numbers, and which is cubic in magnetic vector. So this part is determined by just consistency of the whole construction, because if it's not, because for the you saw in the formula for the completion, we have these generating functions appearing on the right hand side. So one, it's clear that the indices should adapt properly. Yeah, somehow. Get the correct. So essentially, you can get this cubic piece out of this requirement. But the linear piece, unfortunately, it cannot be determined in this way, because any linear function somehow, well, you understand, adapts correctly here.
So by that you mean the tree level cubic term in the thing, in the prepotential, right? That's what you are referring to, right? The cubic kappa ABC TATB TC.
Yes,
that
yes.
one, right? Okay.
Yeah, and the linear term. So we found that it must be fixed by second term class by comparing with Wafa-Witten theory, essentially.
So, I mean, many years ago, when we were around 2001, we were looking at things like this. So there I tried to fix these, not the cubic parts, but some parts I could fix by saying that the O of, so from trying to relate a mathematical formula to a physical formula. So I tried to argue that pure D6 brane should be the O of the manifold, O of the Calabi-Yau 3. And that gave me some conditions which agreed with, you know, the subleading pieces like the ones you're talking about. It came exactly that way. And I never understood why that happened, but it gave the correct answers. And
well,
we did
least, you see, at least here we don't have yet D6 brains. Yeah.
Yeah, I know that. I know that. But what I said, it's not, I mean, it's not like I'm just looking at the, what was I? Yeah, I was just using, so there is one central charge formula in terms of Chern classes, etc. The other one is in terms of the periods, right? And you compare the two. And that gave whatever I have a requirement that a D6 brane wrapping the whole Calabi-Yau should be the, you know, O bundle, O, I mean, the line bundle O of the.
Yeah, of course, there are many relations between different objects here, so it's possible that these two things are related.
Yeah. So that was also a consistency condition, like you're saying that you are also able to determine things. I don't know if they are the same. I don't know. I never understood it then.
We also actually, fixed, how to say it, so that the formula works, although it should be a little bit modified in the cases with high supersymmetry, because you remember I told you that with Suresh-Nampuri we considered applied these results for high supersymmetric cases. And actually, it's a general thing that this formula for the completion has been derived in one particular context, namely compact Calabi-Yau, generic Calabi-Yau, which gives n equal to supersymmetry. Then the four cycles should be ample, namely p cube should be positive, and so on. And then it turned out that the same formula works in a much larger class of cases, like high supersymmetry. You can drop the requirement that the divisor is ample. For example, p cube can actually be 0, not necessarily positive. So there are some degenerate cases which still captured by that formula. But they should be properly understood. In particular, when you go to high supersymmetry, it turns out that this quadratic form kappa, which is here, so in our case, in the usual case of ample divisor, this is a non-degenerate quadratic form, although indefinite signature, yeah? But it's non-degenerate. But when you go to high supersymmetric cases, so to the case of non-ample divisor, it becomes degenerate. So it can have certain zero eigenvalues. And then, in particular, this affects the index. So, roughly speaking, the index should be determined by only non-degenerate part of that quadratic form. And also, you should subtract the number of zero eigenvalues, roughly speaking.
Oh, okay. That's very interesting.
Yeah. So in the with Suresh, we gave a general formula for the index, which is supposed to hold in generic situations.
Thank you.
Hi, Sergey. Very nice talk. So, can I ask something? So, is there a direct implications of this higher depth modular forms in direct CFTs? I remember a couple of years back, Miranda Cheng and others, someone essentially had a large class of CFTs and modular forms for them, but probably they were not of the higher depth.
Well, the high depth it does appear. I remember there was a paper of Samir, for example, where they did appear, but I'm not sure it's what you the same things which you meant. In the paper of Samir, it was a study of certain index related to n equal 4 super n Mills. No, sorry. No. It was some. No, it was. Sorry. No, it's different. It was some. Yeah, I forgot. Yeah, there was some CFTs obtained by.
Ferrara and Miranda Cheng.
Sorry.
I think Ferrara.
No,
Ferrari, you mean Ferrari?
They constructed some twisted.
No, not Ferrari. She's from Shisa, so she just was the first postdoc was with Miranda, the second postdoc was with Miranda. Yeah, she also with,
can you specify the question precisely? What?
Yeah, when I remember there was this paper by Miranda Cheng and this girl. So essentially, they basically constructed a lot of CFTs, and then they are basically the partition functions and etc. Were expanded in terms of various modular forms. But if I remember correctly, those were some H-taus basically. So they were modular forms, but they were probably not of higher depth. So I'm asking, because you are working with higher depth modular forms, can I have direct implications on, or can I have CFTs which directly will have this?
Well, I'm not sure I'm aware of those papers, therefore it's difficult to say for me. Or yeah, maybe just yeah, I don't know the precise context, so
Sure.
I cannot say something concrete. But in general, yeah.
But in general, is this possible to use this higher depth things in CFTs directly?
Yeah, sure. And they have been used, I think, as I mentioned I think in some of Samir's papers, they appeared. And just generically, I think, well, there should be some Well, typically, mock modularity appears as when your CFT is non-compact. Yeah. So, and you have continuous spectrum in the game. So, I think if you, complicate enough your CFT, you should also see high depth objects. So roughly speaking, something should be decomposed not into two components, but to more components. Once you have several components, you will have this high depth.
So usual CFTs with some finite number of primaries will not give anything like this. Right?
Yeah, you need the infinite spectrum, continuous spectrum, typically, for mock modularity.
Right.
Yeah, and also you need typically you get mock modularity once you have this indefinite theta series. As soon as you have somewhere indefinite quadratic form, so then the depth will be essentially determined by the number of minuses in this quadratic form.
Okay, thanks, Sergey.
Okay, so if there are no further questions, let us thank Sergey again.
Thank you very much, Sergey.
Thank you. Thank you, Sergey.
Okay, so I close the recording now.